In this video, we are briefly discussing about the introduction of digital logic circuit. In the digital logic circuit, implement digital logic functions such as NOT or AND gate. This is a symbol of digital logic, and this is a timing diagram. This is a truth table of each logic function. So as you can see, further this logic function can be implemented as only two different binary value, which is logic value 0 and logic value 1. So to express this digital function, we need the digital logic circuit. By the way, digital designers often use the word low and high voltage in place of logic value 0 and the logic value 1, which is the low voltage of electric signal means that logic value 0, high voltage electrical signal indicates logic value 1. So this is called as positive logic, but the opposite expression is going to be called as a negative logic, which is going to be logic value 1 is expressed by the low electrical signal or the low electric voltage. The zero logic value 0 is going to be expressed as a high electrical signal or high electric voltage. So as a summary, we can say digital logic refers to the values of electrical signal, which is going to be low and high voltage. So low, in this positive logic, we can say low voltage indicate logic value 0, high voltage indicate logic value 1. So how do we gonna implement this electrical signal as a digital logic function? So there are so many technologies has been proposed and introduced and commercialized. So for example, if we employ the fiber optics technology to implement this digital logic function, so we're gonna just employ the light on and off. If the light is off in the fiber optic system, it indicates logic value 0. If the light is on in the fiber optic system, which means that the logic value 1 in the digital logic function. However, so the mostly widely used technologies in the industrial semiconductor companies, they are adopting the CMOS logic, which is called complementary metal oxide semiconductor. This CMOS is composed of the NMOS and the PMOS, which is going to be complementary each other. So we're going to talk about details in the next slide. So by using NMOS and PMOS in one fabrication step, so we can minimize the fabrication cost, and eventually we're gonna make the digital logic circuit chip speed is gonna be a lot faster if you're using the CMOS because they are complementary each other. So in this case, these transistor, by the use of a transistor, so we're gonna use this transistor as a switching system, switching device. So to turn on the switch, we need the voltage. To turn off the uh, switch, we also need the voltage range. So to express the logic value 0, we're going to accommodate this very low voltage range, which is going to be ranging from the 0 to 1.5 volt. However, so to turn it on this transistor to indicate logic value 1, we need a lot higher voltage to turn on the transistor, which is requires 5 volt, which is highest. But if we can consider the noise margin, so we can actually accommodate 3.5 to the 5 volt voltage range, allow us to turn on the transistor itself. So let's talk about more about CMOS logic. As I said, CMOS is composed of NMOS and the PMOS. So which is gonna be the complementary each other. This is NMOS, this is PMOS. Of a cross-sectional view. This is a CMOS cross-section in the perspective of fabrication. CMOS cross-section. Because MOSFET is a transistor which is operated by the field effect. This field is an electric field. This electric field is gonna be provided by the input voltage. Input voltage. So how do we apply this input voltage as a data input? Data input. We need the input terminal. So as you can see, for the MOSFET and the PMOSFET, they have 3 different terminals, which is a gate, drain, source, or source and drain. The most important terminal in MOSFET is a gate, because gate is an input terminal. So by applying the input voltage to the gate, we can actually turn on the transistor if the gate voltage greater than the threshold voltage. For the PMOSFET, it is gonna be the different polarity. That's why they do have a different polarity range for the gate source voltage. So in this case, why is different between MOSFET and PMOSFET? Because they are different main current carrier, which is of electrons for the MOSFET, holes for the PMOSFET. So in terms of a major current carrier, electrons are a lot faster than hole. So MOSFET is gonna be a little faster operation speed compared to the PMOSFET. For your information. Okay, and back to the CMOS logic. So as we knew, most transistors, metal oxide, semiconductor transistor, which is called MOSFET. This is transistor, this is field, this is effect, field effect transistor. which is acting as electrically controlled switch. Specifically, can be can we say voltage controlled switch. They do have three different terminals: source, drain, gate, which is a gate is an input terminal. So you can simply express the CMOS logic. For the NMOS, they are passing the logic value 0, where for the PMOS, they are passing the logic value 1, where compared to the NMOS. So this operation is vice versa between the NMOS and PMOS. So when the NMOS is on, the logic value 1 is going to be expressed. When the PMOS is on, logic value 0 is going to be expressed. But in this case, to turn on the voltage, to turn on the transistor, this transistor, they require the required magnitude of voltage to turn on the transistor. So how high or how high magnitude is required to turn on the transistor, to turn on the MOSFET? At the beginning stage, at the initial stage of microelectronics in 1980s, the sufficient voltage magnitude is usually 5 volt. So this is a supply voltage to turn on the transistor, to turn on the MOSFET, turn on. But this supply voltage, which is VDD, has been decreasing because the industrial technologies, which is semiconductor technologies, has been growing so fast. Chip miniaturization is allowed to us to decrease the VDD from 5 volt to the almost 0.7 voltage range. For the 5 volt, so this transistor size itself is going to be centimeter range, but the 0.7 volt range for the VDD, this transistor size is going to be nanometer size. The centimeter size compared to the nanometer size, nanometer size, it's going to be the 10 times 10 bigger. Am I right? Millimeter. No. The centimeter size is gonna be the, yes, millimeter. Anyway, fine. Nanometer size is a 10 minus 9 meter. Okay, the centimeter is gonna be the 0.1 meter, which is gonna be, sorry, 10 over minus 1, about 10 over 8 times bigger. Yes. So that's why, so we can decrease the VDD, which is supply voltage, so which allows to have biggest advantage, which is a lower power consumption of CMOS logic digital circuit, which is very crucial to maintain the high capacity of calculations, to improve the computer capabilities, this kind of thing. So let's continue to the simple basic building block of CMOS, which is CMOS inverter in the next video. Okay, thank you.